Right. So in this class, we'll be discussing about some special purpose diodes, photodiode, LED, and solar cell. Uh, can any of you tell me what a photodiode is used for, or what is its basic function? So it's a device which gives you an alert, or which sounds an alarm when light falls on it. Light of a particular wavelength falls on it. Okay, particular wavelength or a small range of wavelengths. So you can say it's like a light detector or radiation detector. Fine. How does it work? See, a photodiode is basically a PN junction, but in reverse bias. Now, how much current flows through a PN junction in reverse bias? How much current flows through a PN junction in reverse bias? Fine. Basically, in reverse bias, the current through a junction is negligible. In an ideal case, we take it to be zero. Okay. Now, consider a PN junction like this. Just a moment, let me draw the circuit completely. Right. So this is the P side, this is the N side. To make the PN junction reverse biased, you have to connect the higher voltage to the N side and lower voltage to the P side. So negative terminal to P, positive terminal to N. Now it is reverse biased. Basically, what happens in reverse bias, the depletion region will widen. Okay. It will be difficult for electrons to diffuse from N side to P side or holes to diffuse from P to N. The drift process will be dominating. Okay. What do we mean by drift dominating? The electric field in the depletion region will be very strong. Okay. In reverse bias. But in reverse bias, there is no significant current through the circuit. Okay. Or through the PN junction. Now, if we connect a small speaker here, okay, a speaker or a beeper, basically it produces a sound when current passes through it. Now the diode is reverse biased. In reverse bias, there is negligible current, so the beeper will not produce any sound. Fine. Now you need to understand why the current in reverse bias is negligible. Basically, in reverse bias, as I said, the electric field in the depletion region is very strong. What will this electric field do? What will any electric field do? It will exert force on charges. Okay. In the depletion region, there are no free charge carriers. Okay. There are electrons, but they are present in the bonds. They are in the valence band. If there is any conduction electron, then the electric field can show its effect on it. Okay. On a valence electron, electric field will not be that strong to pull out the valence electrons. Okay. So what happens is occasionally an electron hole pair will form in the depletion region. What do we mean by that? An electron may jump. Okay. Occasionally an electron may jump from the valence band into the conduction band. When an electron jumps into the conduction band, automatically a hole will be left behind. Now, what this electric field will do is, as we have discussed already, the electric field will bring the electron back to the inside by, by exerting a force on it. Okay. And it will push the holes to the P side. That is what happens in the depletion region. And if electron comes to the N side, means negative charge moving from P to N, it means current flowing from N to P. Okay. And if hole is pushed to the P side, means positive charge is going to the P side. That also means current flowing to the P side. This is what we call as drift current. So basically in reverse bias, drift current dominates, but drift current will be negligible. Why is it negligible? Because drift current is due to minority charge carriers. Like electrons have to come from P to N, but P is called P because holes are dominant there. Holes are the majority charge carriers on the P side. Very rarely you'll find some conduction electrons. That happens when a valence electron jumps into the conduction band. That is not very frequent. Okay. So drift current is negligible. That is why reverse bias current through a PN junction is negligible. Okay. Now by some means, if you can increase the production of these electron hole pairs in the depletion region, then you can increase the reverse bias current. Because if more electrons jump from valence band into the conduction band, then the electric field will be pulling those electrons, will be pulling more electrons to the inside. It will lead to a rise in reverse bias current. Okay, that is the principle behind the working of a photodiode. So if you consider a normal PN junction in reverse bias, the current through it is negligible. And because the current is negligible, this peaker or beeper that is there will not produce any sound. Okay. So you need to increase the production of electron hole pairs to get significant current in reverse bias and to switch on this speaker or to make the speaker make some sound. Okay. Now, how to increase the number of electron hole pairs? Now, we had discussed something called energy bands. When does an electron hole pair form? When an electron jumps from the valence band into the conduction band. Now, in a semiconductor, between the valence band and conduction band, there is a small energy gap. If you can somehow supply energy to the electrons and help them jump from the valence band into the conduction band, then you can create electron hole pairs. Okay. And to make them jump from valence band to the conduction band, you need to supply energy which is equal to the energy gap of that particular semiconductor. Okay. Suppose a particular semiconductor has an energy gap of 2 electron volts. What does energy gap mean? It's the difference in energy between the it's the difference between the highest energy level of the valence band and the lowest energy level of the conduction band. That difference in energy is what you call as energy gap. So suppose there is a semiconductor whose energy gap is 2 electron volts. Okay. For example, let the energy gap be 2 electron volts. Then if you can somehow supply this 2 electron volt energy to the electrons which are in the depletion region. What are the electrons in the depletion region normally doing? They are in valence band. They participate in bonds. Okay. If you can supply 2 electron volt energy to them, they will jump into the conduction band and then this electric field will create a current. It will pull the electrons back to the inside. So all you need to do is create those free electrons. Okay. How can we supply energy to electrons? There are many ways by which you can supply energy to electrons. One way is by making radiation incident on it. Okay. So corresponding to 2 electron volt, you make radiation incident on it. So if the energy is 2 electron and making radiation incident means what? Supplying the energy to electrons by means of photons. Now, how do you calculate energy of a photon? Hc by lambda. So for 2 electron volt, the required wavelength of radiation, you know Hc is 1240 electron volt nanometer divided by lambda in nanometers. So the wavelength of radiation that must be incident in nanometers would be 1240 divided by 2, that is 620 nanometers. 620 nanometers is it's in the visible range, no? 400 to 700 nanometers is visible range. So 620 nanometers corresponds to maybe orange color. Okay, YOR, yeah, orange. Red is close to 700. 620 will be about orange. So basically, if there is a PN junction made of a semiconductor whose energy gap is 2 electron volts or around 2 electron volts, In reverse bias, it won't produce current normally. But if radiation is incident, and where should it be incident? Radiation should be incident on the depletion region. Fine. And we found that for 2 electron volt, the wavelength of radiation required is about 620 nanometers, which corresponds to orange color. So if orange colored radiation is incident on the depletion region, what will that lead to? It will lead to creation of a large number of electron hole pairs. So you will see a lot of conduction electrons being produced in the depletion region, and a lot of holes also being produced in the depletion region. And if there are a lot of charge carriers present in the depletion region, it will give rise to significant reverse bias current. Okay. So once the radiation is switched on, the drift current becomes significant. Means the reverse bias current becomes significant. Okay. Electron is going from P to N, means current is going from N to P. So a lot of current starts flowing this way. And if current flows through this circuit, the speaker will make a sound, or the beeper will make a sound. So the alarm will get switched on. So whenever light falls on the diode, okay, whenever light of what do we say, appropriate wavelength, whenever radiation of appropriate wavelength falls on the PN junction, okay, depletion region of the PN junction, significant current will start flowing through it. Okay, but remember, it has to be reverse biased, because when there's no radiation, we don't want there to be any current flowing. Okay, that's why we make it reverse biased first. The moment radiation of appropriate wavelength falls on it, you will see current flowing in this circuit. You may make a speaker sound, or you may connect a small bulb which will light up, okay, just to alert. Now, photodiodes, these are used in gaming systems, these are used in burglar alarms, these are used in smoke detectors also. Okay, see, for what wavelength the electrons jump into the conduction band depends on the energy gap. Okay, so you can choose materials having different energy gaps depending on the wavelength that you want to detect. Okay. So that is how a photodiode works. So the points you need to remember are that it is operated in reverse bias. And in reverse bias, normally the current is negligible. But if radiation of appropriate wavelength is incident on the depletion region, you will be generating a lot of charge carriers, conduction electrons and holes in the depletion region. That will lead to a significant amount of reverse bias current. Next, LED. LED is basically a light emitting diode. These days, LED based LED bulbs are very common. Basically, as the name suggests, what an LED must do is emit light. Okay, you can use diodes to produce light. Now, how can a diode produce light? Production of light means release of energy. How can a diode release energy? Listen, let's again consider a semiconductor which has an energy gap of 2 electron volts. Okay, we know that radiation of energy 2 electron volts corresponds to orange color. Radiation of this energy corresponds to orange color. Okay, let's say there is a semiconductor whose energy gap is 2 electron volts. Fine. Now, basically, LED should produce light whenever current passes through it. When you switch it on, it should produce light. When you switch it off, it should stop producing light. So, how does it do this? LED, light emitting diode, is based on a heavily doped PN junction. Okay. What do we mean by heavily doped? There should be a large concentration of charge carriers on the P side as well as the N side. It's very important that it is heavily doped. You'll understand why. Okay. Now, PN junction, which is unbiased, will have zero net current through it. Diffusion current, drift current will balance, net current will be zero. Let's say this is an unbiased PN junction. Now, when you connect it to a voltage source, let me just draw the circuit diagram. Assume the switch is open, and when the switch is closed, you can make the PN junction forward biased. Okay, the circuit is arranged in that way. LED is operated in forward bias itself. Okay. Now, when the switch is open, the net current through the PN junction is zero. Fine. Now, remember, it is heavily doped, means there are a lot of free electrons, conduction electrons on the N side, and there are a lot of holes available on the P side. Fine. When you close this switch, basically you're making the junction forward biased. And in forward bias, what will happen? The depletion region will become narrow. Diffusion process will dominate. What happens in diffusion process? Electrons go from N side to P side. Fine. And holes diffuse from P side to N side. Now, when an electron goes from N to P, negative charge going from N to P means current going from P to N. And when hole diffuses from P to N, positive charge going from P to N, that also results in current moving from P to N. Okay. So forward current will be there. And you know that through a PN junction, once the applied voltage is greater than the knee voltage, there will be significant forward bias current. So the current is significant. Okay. How does it produce light? Now, when electrons from the inside, conduction electrons, what are conduction electrons? High energy electrons. Okay. Let me just copy that energy band diagram just a moment of semiconductors. Fine. So in semiconductors, there's an energy band or energy gap of around 0.2 to 3 electron volts. Now, when electrons move from n side to p side, these electrons are conduction electrons, means high energy electrons. They are in the conduction band. So consider an electron in the conduction band. On the p side, there are a lot of holes. Holes are basically vacancies in the bonds. Now, we considered heavily doped PN junction. So there are a lot of electrons which will diffuse from N side to P side. If a lot of electrons diffuse, there are higher chances of collisions between the electrons. Okay. As a result, what could happen? Many electrons will lose their energy. Now, what happens if a conduction band electron loses its energy? It comes down to the valence band. Okay. Now, on the P side, there are holes ready to accept the electrons. Hole is a positively charged entity. Okay. Suppose a conduction band electron during a collision loses energy, then what will happen? It will fall down into the hole or it will settle in the hole. So electron hole recombination occurs. Just a moment. This will happen in a normal diode also. In an LED, this will happen more frequently because it is heavily doped. Okay, so there are greater chances of this happening. Now, when an electron hole recombination occurs, conduction band effectively jumps down to the valence band. When it jumps down to the valence band, it will have to release the energy. Whatever is the energy gap that is there, it will have to release that much energy. Now, suppose you consider an LED made of a semiconductor whose energy gap is 2 electron volts. Then whenever a conduction electron comes down to the valence band, it will release a photon whose energy is 2 electron volts, means it will release orange colored light. Okay, that is how an LED works. So LED is operated in forward bias itself. Okay, we want significant current. Only then significant amount of light can be produced. You need a lot of electrons diffusing from N side to P side and settling in the holes. Same with the holes also. There will be a lot of holes diffusing from P side to N side and accepting the electrons there. Okay, so LED works on the basis of electron hole recombination. For that to happen, you need heavily doped PN junction operated in forward bias. Okay, whenever an electron hole recombine, it will produce or it produces light. The energy is released in the form of a photon. That is how an LED works. Now you have LEDs of different colors. How are LEDs of different colors produced? See, each color corresponds to a particular wavelength, and each wavelength corresponds to a certain energy difference. So by choosing appropriate semiconductors, suppose you want an LED which produces red colored light. The wavelength for red color is close to 700 nanometers. Okay. That means the energy of a photon, which corresponds to red colored light, will be hc by lambda. Hc is about 1240 electron volt nanometers divided by the wavelength needed is 700. So 124 by 70, it will be approximately 1.9 electron volts. So you choose a semiconductor or you prepare a semiconductor whose energy gap is 1.9 electron volts. Okay. Now, see, elemental semiconductors like silicon, germanium, they have a fixed energy gap. But by combining many elements, fine, you can create an energy gap that you need. A single element will have a single energy gap between valence band and conduction band, but combining a few elements can give you an energy gap that you desire. Okay, there are some combinations given in your textbook. You can go through them. Uh, Germanium arsenide phosphate, okay, GeAsP. Those three are combined to make a semiconductor, which I mean, which has an energy gap that we need to produce LEDs. Okay. So suppose the energy gap is 1.9 electron volts, then whenever an electron and a hole recombine, that kind of a PN junction diode will produce or will release red colored light. Okay. Now, greater this forward bias voltage, as you increase the forward bias voltage, the current increases. And if current increases, the brightness of light increases. But it can increase only up to a certain extent. Okay. You keep on increasing the forward bias, what will happen? The chances of electron hole recombination, see, up to a certain extent, the electron hole recombination chances will increase. What do we mean by that? Uh, Suppose there is no biasing voltage. Net current through the junction is zero. Okay. Diffusion will happen, drift will also happen, but the magnitude of diffusion current or the magnitude of drift current will be less. If you increase this biasing voltage from zero, if you start increasing it, okay, you will be favoring the diffusion process. So more amount of diffusion will happen, more electron hole combination will happen, then more light will start getting produced. Okay, so the brightness or intensity of light of the LED will increase. But if you increase it too much, then what will happen? The problem is that there will be a lot of current flowing through the diode. That's fine. But the chances of electron hole recombination will decrease because maybe the electrons are moving too fast or some reason. It will become difficult for them to settle down in the holes when the voltage is too high. Okay. So in an LED, as you increase the forward bias voltage, current increases up to a certain maximum and then it starts decreasing. Okay, you need to remember this property of LEDs. Current does not, okay, wait. I should not use the term current. I should use the term brightness of light. Yes, current will go on increasing. As you increase the voltage, current will increase. But the brightness of light that you get, it increases up to a certain maximum and then starts decreasing. Because when the voltage exceeds a certain value, electron hole recombination chances will decrease. And when electron hole don't recombine, they don't produce light. Okay. So as voltage increases, okay, forward bias voltage increases, current, okay, I'm again using the term current, brightness of light first increases, then decreases. Okay. And LEDs are designed to be operated in forward bias. In reverse bias, what will happen? There won't be current, but you know that there is something called breakdown of a diode which can happen in reverse bias. Usually for LEDs, the breakdown voltage, okay, the reverse bias breakdown voltage is very low. It is about 5 volts only. Okay, or maybe less than that also. So you should ensure that the LED never gets reverse biased. If it gets reverse biased, there are very high chances that it will get damaged. Right? You can find LEDs in electrical shops also. You can play around with them. Just connect a battery, it will produce light. But you connect the battery in reverse, it will get damaged. It won't produce light later, even when you connect it in forward bias. Like you can know that it is damaged. Okay. So this is how an LED works. You need a heavily doped PN junction because we want a lot of electron hole recombination to occur. So you need a lot of electrons and holes in the first place. That's why you need a heavily doped PN junction. and it is operated at forward bias because we need significant current to get significant amount of electron hole recombination. Fine. The next device is a solar cell. Very popular these days. Solar cells are basically devices which can produce electricity when light falls on them. Okay. So producing electricity means what? Producing a voltage when light falls on them. How do they work? Again, solar cell is also based on PN junction itself. But we will not be biasing the PN junction because we want the solar cell to produce voltage. We are not going to supply any voltage to it. Okay. Now consider an unbiased PN junction, and let's say there is a bulb connected to it. Fine. Now the net current through a PN junction, which is unbiased, is zero. Diffusion and drift will balance. Net current is zero. The bulb will not glow. Okay. Now you know what a solar cell does, no? When sunlight falls on it, it produces electricity. How does that happen? Now, in a solar cell, you can't use a normal PN junction. You need a PN junction where the N side is very thin. Okay, this is an important requirement that the N side be very thin. So let me adjust the N side here. It should be so thin that most of the N side should be the depletion region itself. Okay, so I'm going to delete all these conduction electrons and adjust the size of the inside. The P layer will be quite thick. See, this is the cross section of the layers that we are seeing. These are not blocks. Fine. The P side and N side, these are not blocks. These are, you have to imagine them like two sheets which are very close to each other. Actually, they are not even sheets which are close to each other. We had discussed the formation of a PN junction. No? On the same semiconductor base, some regions are uh, doped with trivalent impurity. Some regions are doped with pentavalent impurity. So some regions become P type, some regions become N types, and they are very close to each other. Electrons can flow from one to the other. So it's like that. So you can see that there is a thick P layer here and a very thin N layer. Most of the N layer is the depletion region itself. Okay. Now the net current through this junction will be zero. And on the P side, the entire P layer, almost the entire P layer is covered by metal on the other side. Okay, metal is a conductor. Metals are conductors usually. So there is a metal contact. What do you mean by contact? Basically, that is where you connect the wire to the solar cell. Okay. On the N side, see the N layer is very thin, and on top of that N layer, there is a metal contact, but it does not cover the inside completely. Okay, I'll show you another diagram also, you'll understand better. So when you see from the side, this is how it looks. Okay, let me show you another diagram, just a moment. Right. So, so you can see there is a thick P layer here. Fine. On top of it, a thin N layer. Relatively, it is thin. Fine. So that's the PN junction. The P layer is completely covered with a metal back contact. Okay. This is the metal contact. Whereas the N layer, if you see, most of it is left open. And you just imagine metals, what do I say? You just imagine metal wires and a thin sheet of metal here. Fine. But most of the surface of the N layer is open. Only a part of it is covered by this electrode, you can say. Approximately 15% of its surface, 15% of the surface of the N layer is covered by metal. Okay. So cross section, if you see, I mean, if you cut it this way, it appears like this. I drew the same thing vertically. Okay. This is oriented horizontally. I drew the same thing vertically. So this is the P side. This is the N side. P side has a metal contact completely covering it. N side has a metal contact only partially covering it. Okay. Now, why is it important that it's only partially covered? See, the PN junction is not biased. It's neither forward bias nor reverse bias. So diffusion and drift will be balanced. Net current will be zero. Now, when radiation falls on this PN junction, now see, where is the chance for radiation to fall on it? The only place where radiation can fall on the junction is here on the N side because most of it is open. It is not covered by metal. So when sunlight is incident, sunlight or light of appropriate wavelength is incident on the N side, what happens? So basically radiation falls from this side onto the N side. Now N side is mostly depletion region itself. That is why it is kept very narrow. So basically you are making radiation incident on the depletion region. What happens when radiation is incident on the depletion region? Electron hole pairs will get generated. The valence band electrons will take energy and jump into the conduction band. Okay. So when you generate electron hole pairs and you are generating them on the N side, intentionally you are generating them on the N side. Okay. So when an electron hole pair gets generated, what will happen? The electric field which is present in the depletion region will separate them. It will push the hole back to the P side. If it is pushing the hole back to the P side, hole is positively charged, it is going to P side, means there will be current. Okay. That is how basically we are favoring the drift process. Okay. When radiation is incident on the N side, you will be generating electron hole pairs and you will be favoring the drift process. As a result, what will happen? Excess electrons will be left on the N side. Holes will go to the P side. Electrons will be left on the N side. So you are creating a charge separation. And those charges have a chance of recombining through the circuit. So then current will start flowing through the circuit. Okay. So by making radiation incident on the depletion region on the N side, you are producing a current in this circuit. Fine. Basically, what you are doing is you are encouraging accumulation of electrons on the N side, conduction electrons, that too. Okay. And holes will get pushed to the P side, obviously. Then these electrons and holes, okay, holes will not flow through the wire, but these electrons will flow through the wire and that will produce or that will result in a current. So electrons flow this way through the circuit. So this is how a solar cell works. A single solar cell cannot produce, single solar cell means what? A very small PN junction diode. It cannot produce a significant amount of current, but a combination of solar cells can produce a significant amount of current. And a combination of solar cells is what you call as a solar panel. Okay? Those large panels that you see. These days, many people have them on their rooftops also. So this is how a solar cell works. There's an unbiased PN junction, but it is important that the N side is a very thin layer. Most of it has to be the depletion region because the radiation should be incident on the depletion region. For that to happen, the N layer has to be thin. Okay. And most of the N layer has to be exposed such that significant amount of sunlight can fall on it and significant number of conduction electrons can be generated. Okay. That is why the contact means what? The terminal. You have to connect the solar cell to something, not to the bulb or something. So you have to connect wires. So the contact on the inside should be like this, as that most of the surface is exposed. On the P side, it can be completely covered, doesn't matter. Okay. Next thing, the last part of this chapter is logic gates. See, the main advantage with semiconductors, especially PN junction, is that you can control the current flowing through the junction. Fine. And if you can control current, you can make circuits which produce certain kind of output when a certain kind of input is given. Okay, so you can implement logic in a circuit. Basically, what does logic mean? Based on the input, you have to give the output. You have to understand, like, you have to process the input and give a give an appropriate output. That is what logic is. So you can implement that in a circuit by using diodes. Right? And devices which are made of a combination of diodes and which give a particular output based on the input are what you call logic gates. Okay. There are 5 gates in your syllabus. You just need to understand the basic behavior of these gates. You don't even need to know the circuit which is used to make these gates. Okay. To understand how a logic gate is actually designed, you need to learn about transistors. Okay. As of now, transistors is not in your syllabus. It is there for advanced. Okay. For mains boards, it is not there. So we will not be discussing. If required, we will discuss later for advanced. Okay. Potentiometer in current electricity, X-rays in the chapter atoms, and transistors in this chapter. These are the 3 topics which are exclusively for, okay, radioactivity in nuclei also. So potentiometer, X-rays, radioactivity, transistors. These 4 topics are exclusively for advanced. Okay, so we'll not be discussing them as of now. If required, we'll do it later. Now, there are basically 5 types of logic gates, devices which give a particular output based on input. Fine. You just need to know for what output, for what input, what kind of output they produce. The first one is a NOT gate. See, these are all logic gates are all used in digital circuits, right? Basically to make electronic devices. Now in digital circuits, basically the circuits that you find or the chips that you find in mobile phones, computers, television sets, TV remotes, these are all digital circuits only. In digital circuits, the signals are given in the form of zeros and ones. Okay, binary, what do you call, signals. 0 indicates low voltage, 1 indicates high voltage. Okay. So an analog signal means a normal AC signal looks like this. You will see an alternating voltage, increasing and decreasing voltage, which continuously increases and decreases. Okay, like E is equal to E naught sine omega t. Right? So this is what an analog signal looks like. But a digital signal will have only zeros and ones. Low voltage indicates 0. High voltage indicates 1. How high is high and how low is low? Usually 5 volt and above is considered as high. Less than that is considered low. Okay. So when there is a voltage of 5 or above, you will get a signal which is, you'll get a high voltage signal which is 1, which is considered as 1. And when the voltage is less than that, you get a signal 0. Okay. So this is what the digital signals look like. There will be a combination of zeros and ones. Okay. Now, the first gate that you need to know about is a NOT gate. Basically, what a NOT gate does is it negates the input. What do we mean by negating the input? The output will exactly be the opposite of input. Okay. The symbol for a NOT gate is this. You need to remember the symbols. A triangle with a circle in front of it. Okay. And it has a single input and a single output. Suppose A is the input and Y is the output. Now in digital signals, there are only 2 inputs that you can give, a 0 or a 1. Fine. So suppose A is 0, then Y will be 1. If the input is a low voltage, output will be a high voltage. Okay. How it can do that? As I said, you need to know the working of a transistor. Okay. The NOT gate needs a power supply to do that. When you give a 0 voltage, how can it give 5 voltage as the output? There should be some other power supply. Okay. In a transistor, there are biasing batteries that we use. They will help in producing that voltage. So when input A is 0, the output Y will be 1. And when input A is 1, output Y will be 0. This is what a NOT gate does. Okay. And this table that you draw showing all possible inputs and outputs, okay, all possible inputs and corresponding outputs of a logic gate. This table is called its truth table. Okay, so basically it's just a table which shows all possible inputs and all possible outputs of that gate. Okay, so for a NOT gate, this is the truth table, and that is what a NOT gate does. It just negates the signal. Negates means produces the opposite of the input signal. So if input is 0, output is 1. If input is 1, output is 0. Okay. Next is an OR gate. OR gate is a gate with two inputs and one output. Okay. Inputs you can call as A and B. Output take it as Y. Now what does an OR gate do? Whenever at least one of the inputs is a high voltage, the output will be a high voltage. Okay. So either A or B or both of them. Okay. If any of those is 1, the output will be 1. But when both A and B are zeros, the output will be 0. Okay. So one of them has to be high, then the output will be high. So how will you draw the truth table? Now see, there are two input signals to an OR gate, and each input signal has two possible values. Okay. So two inputs with each of them having two possible values. So there will be a total of four input combinations. Output is Y. Okay, there are symbols also for this. In the NOT gate, the output is the opposite of the input, right? Negation of the input. So we write Y is equal to A bar. Bar indicates negation. Okay, so Y is the opposite of A. Now in an OR gate, either A or B or both have to be high, then the output will be high. In case both are zeros, the output will be 0. We represent an OR operation like this. Y is equal to A plus B. You are supposed to read it as A or B. Okay. The plus doesn't mean anything. It is just a symbol used to indicate that it's an OR operation. Okay. Don't actually add the signals A and B. So when A is 0 and B is 0, the output will be 0. But when A is 1, B is 0, the output will be 1. A is 0, B is 1, the output will be 1. And when both are 1 also, the output will be 1. This is what an OR gate does. Okay, this is the truth table of an OR gate, and the symbol for OR is plus. Right. Next is a NOR gate. Okay. N stands for negation. So NOR gate is basically negation of OR. Okay, so it produces the opposite signal of an OR gate. The symbol for an OR gate, there's only a small difference between the symbol of OR and NOR gates. Just a circle in front of the curved D. That's all. This is the output Y. Now, output is the negation of A or B. So, the operation is denoted like this: A plus B whole bar. Okay. Truth table, it will just be the opposite of the OR gate truth table. So basically what happens whenever A is 1 or B is 1 or both are 1, the output will be 0. Only when both are zeros, the output will be 1. Y in this case is a plus b whole bar. When a is 0, b is 0, the output will be 1. In all other cases, it will be 0. Okay. Next is AND gate. AND gate gives a positive output only when both the inputs are positive. And the symbol looks like a proper D with two inputs and one output. The operation A and B is denoted by A dot B. Okay, you read it as A and B. So what happens in an AND gate? When both inputs are ones, you get the output as 1. In all other cases, the output will be 0. So A0, B0, Y will be 0. A1, B0, output will be 0. A0, B1, output will be 0. Only when both are 1, the output will be 1. Okay. Next is the last one, which is a NAND gate. As the name suggests, it is the negation means opposite of AND gate. There's only a slight difference between the symbol of AND gate and NAND gate, that extra circle in front, that's all. Circle basically indicates negation. Okay. Now, this time the output is the opposite of AND, so it will be A plus B whole bar, negation of A and B. Okay. And truth table is just the opposite. The output is just the opposite of that of AND gate. So if A is 0, B is 0, their AND value will be 0, NAND value will be 1. If A is 1, B is 0, AND value is 0, NAND is 1. Again, same with this. A is 1, B is 1, AND value is 1, NAND will be 0. Okay. Now, you may be asked simple questions based on the combination of these gates as well. For example, let's consider a circuit like this. Suppose there is AND gate. Let's call this signal as A, this signal as B. The output of the AND gate and the signal B. Okay. Now you can give the same signal as input to multiple gates also. Okay, that is possible. So the output of the AND gate and the signal B, suppose they are given as input to OR gate. And you take the final output here, Y. Okay. Draw the truth table of this combination. What do we mean by truth table of this combination? For different possible combinations of A and B, what will be the output Y? Okay. Now A and B are two input signals. Each input signal has two possible values. So there will be four different combinations of input signals. Okay. So for all four input combinations, you have to you have to calculate the output. Do this, all of you. I'll give you the input combinations. You just type the output in the answer. Both zeros, A1, B0, A0, B1, and both ones. For each possible input combination, what is the corresponding output? Type your answers in chat. I'll give you all 2 minutes. Okay, I got two answers. Let's see. Now, A and B, okay, this is an AND gate, obviously, and this is an OR gate. Fine. Let's consider the first input. A0, B0. If A and B are zeros, the output of the AND gate will be 0. The same signal B, which is 0, is given as input to the OR gate. So 0 and 0. Okay, this is 0 and this is also 0. B is 0. 0, 0 as inputs to the OR gate, the output will be 0. Next. A is 1, B is 0. If A is 1 and B is 0, their AND output will be 0. Okay, that is one of the inputs to the OR gate. And B0 is the other input to the OR gate. So both zeros, again the output will be 0. Next, A is 0 and B is 1. Let's see. If A is 0, B is 1, and output will be 0 itself. So that upper signal will be 0 only. The lower signal, okay, the second signal to the OR gate is 1. 0 or 1, the output is 1. Next, A is 1 and B is 1. If A is 1, B is 1, the AND gate output will be 1. That will be given as one of the inputs. The other input is also 1. 1, 1, OR value is 1. Okay, so this is the truth table of this circuit. So by combining gates, you can make new gates. Okay, see what you made here. You made, okay, actually this combination is a useless combination. Basically what you did, see the output. Whatever is the value of B, you get the same as the output from this gate. Okay, so basically, why did I say this gate is useless? You could have directly taken B's value. Okay, you could have directly taken B as the output. Why design all this gate? Okay, but anyway, there are some combinations which can help you design new gates also. Right? Questions like this are very common. Let's try one more question. This is last year's JEE main question. Okay, try this all of you. They want you the values of X and Y in the truth table. Means they want you to find out output in cases when A is 0 and B is 1, and in case where A is 1 and B is 0. Other outputs they have already given. Do this. Identify the gates properly first. One of you tell me, what gate is this?
NAND AND gate, sir.
Yeah, it is an AND gate. See, if this line is straight, it's an AND gate. Okay, if the line is curved, it becomes an OR gate. Okay, this is AND. What are these gates? These small ones. Triangle with a circle
AND
in
and
front.
NOR.
Eh? The
They're the
small
same.
ones. These are not gates. Triangle with a circle in front of it. Not and not. Okay. This is AND again. And this is OR with a circle in front of it. So effectively it becomes a NOR gate. This whole thing is a NOR gate. Okay. Now take the given inputs and write the output. If you have any doubts, you can ask in identifying the gates. Okay, let's see. Let's consider the first combination A0 and B1. Okay. When A is 0, B is 1. See, wherever there is an output, let us give some name to it. Let's call this output as P, this as Q, this as R, this as S. P and S will be the inputs to the NOR gate, and finally E will be the output, final output. Okay. When A is 0, B is 1, what is P?
Zeros.
0. Okay. 0 and 1, the output is 0. Now, you see, A is connected to one NOT gate and B is connected to the other NOT gate. Now, Q is just the opposite of B. Okay. Q is just the opposite of B, means Q is 0. R is just the opposite of A, means R is 1. Okay. 0, 1, the AND output will be 0. 0, 0 are given as inputs. Okay, P is 0, S is 0. These are given as inputs to the final NOR gate. If 0, 0 are inputs to the NOR gate, then the output will be 1. Okay, so X becomes equal to 1. That is how you solve such problems. Next, if you want Y is the output when A is 1 and B is 0. A is 1 and B is 0. If A is 1, B is 0, P will again be 0. And Q, which is the opposite of B, will be 1. R, which is the opposite of A, will be 0. 1, 0, and value is 0. Again, 0, 0 as inputs to the NOR gate, output will be 1. Okay, so Y is also equal to 1. Sometimes you can be given questions like this also. Consider a simple circuit with two switches in it. Okay, battery, bulb, and two switches. Switches are named A and B. When a switch is open, we treat it as 0. And when a switch is closed, we treat it as 1. And when the bulb glows, okay, it is treated as 1. When bulb does not glow, it is treated as 0. Okay. So let's let the bulb be the output, AB be the input signals. Okay. Now both are open. When that means when A is 0, A is open, B is open. Will the bulb glow? Obviously not. So Y is also 0. The output is 0. Now tell me, when A is 1 and B is 0, what is the output? Switch A is closed but B is kept open. What happens to the bulb?
Doesn't glow.
Doesn't glow, circuit is open. Okay, when only one switch is closed, that's not enough for current to flow. So the bulb does not glow. The output is still 0. Similarly, when A is 0, B is 1, also the output will be 0. But when both are ones, means both switches are closed, then the bulb will glow. So when A is 1 and B is 1, the output will be 1. So what does this? I mean, this circuit is similar to which gate? You see the truth table and tell me this circuit is similar to which gate? A0, B0 is giving output 0. A1, B0 is giving output 0. A0, B1, the output is 0. Only when both inputs are 1, the output is 1. Which gate does this? This is very easy. Think carefully and answer quickly. This is an AND gate. It's like Y is equal to A and B. When any one of them is 0, the output is 0. Okay. But when both are ones, the output is 1. So this is what an AND gate does. So this is similar to, this circuit is similar to an AND gate. So you can be asked questions like this also. And okay, look at this question, which was asked last year. They gave a network of gates and they are asking you what is the output of the following circuit of inputs. Okay. Now, they are not asking you for the truth table, but they are asking you what is the resultant operation of this gate? What is the effective operation that the gate does? Okay. This I think is typed wrongly. A dot B. Okay. There should be something here like a dot or something. Let it be. But how will you solve or how will you answer questions like this? You are given a network of gates and you are asked what is the equivalent output. What will you do? Okay. One way to do it is write the truth table first. Okay. Consider all possible inputs for A, B, and write the outputs. A0, B1, what happens? A1, B0, what happens? When both are zeros, what happens? And when both are ones, what happens? Now, this output that you get, it has to match with one of these. So, what you will have to do is you will have to write the outputs of all the options. Okay. Generally, see, A dot B means it's an AND gate. For AND gate, you know the output combinations, no? Write that. Try to match. If it is matching, this is the correct answer. Or A bar dot B. Write the truth table for that operation. And if it is matching with this one, then that is the correct option. That is one way to do it. Okay. But there is a better way to do it also without writing the truth table and all. Do you all know De Morgan's laws? In mathematics, you must have learnt. Like in sets. What is A union B whole bar?
So all elements of A and B combined.
That is A union B. All elements of A and B combined. What is A union B whole bar? You didn't learn De Morgan's laws in mathematics. Like that bar, I think is read as complement. What is A union B whole complement?
Oh, sir, anything but all the elements of A union.
So how is it written? I mean, symbol. How will you write the symbol for it? Okay, let me take help of this diagram from Wikipedia. Simple. A union B whole bar, okay, is A bar intersection B bar. Okay. Now, how do we use this in logic gates? Union is like OR. Fine. See, when will an element be present in A union B? It should either be present in A or in B or in both. Then it will be in the union. Okay. So it's like union is like OR gate. Fine. Intersection means it should be present in both the elements. Right. Intersection is like AND gate. Fine. So A union B whole bar is equivalent to A bar intersection B bar or A complement intersection B complement means A or B whole negation is negation of A and negation of B. Next, intersection indicates and. A and B whole bar means negation of A dot B is negation of A plus negation of B. Means negation of A or negation of B. Okay. These are De Morgan's laws which can be used in logic gates as well. Let's try to do this. Apply this. Now, this is an OR gate. What are the inputs given to it? A is one input given to it. Negation of B is the other input given to it. So basically what this OR gate is doing is A or negation of B. Okay, let it be. That's the output that you get here. A or negation of B. That's fine. Next, this is AND gate. And what are the inputs given to this AND gate? One input given is B directly. The other input given is negation of A. So this is doing negation of A and B. That is the output, okay, of this gate. Fine. And then what is happening? This is an AND gate, right? The last one is an AND gate. So basically what you are doing is A plus B bar and A bar and B. Okay, how to simplify this? Try to use De Morgan laws and tell me the answer. So how do you write this in terms of sets? Plus indicates union, dot indicates intersection. So I want you to write the output of this. So you think of it this way. A union B complement intersection A complement intersection B. What is the output? Okay. I'll give you all 2 minutes. Think about it. Okay. Tell me this first. How do you express A union B whole intersection C? Or how do you simplify this? See, A union B means it should be in either A or B in both or in both. And intersection C means it should also be in C. So, like, I don't know how to explain set theory, but
So
ah,
both we find the all the elements of A and B first, and then find the common elements in C and A union B.
ah. So either A should have something in common with C for the output to be non-zero. Okay. What you said is correct only. So for the final output to be non-zero, A should have something in common with C, or B should have something in common with C, or both of them can have something in common with C. So how do you write this? A intersection C means this will take care of A having something in common with C. B intersection C, this will take care of B having something in common with C. Both also can be possible. So this is the output. Okay. Plus means union. So in set theory, you should write it as union. Or should it be AND? No, it should be. So A union B intersection C. A union B includes everything which A and B have. Intersection C, if you want the output to be non-zero, everything which A and B have, at least some of them should match with C. So anything of A can match with C, anything of B can match with C. In both cases, the output should be non-zero. So A intersection C union, B intersection C. I think this is correct. Just check it once and tell me, is this how it is or not? I think this is correct. So you can write it as like the above one. You consider this as C now. So you can write it as this pen is suddenly becoming extra sensitive. I don't know why. Okay. So you can write this as A intersection C. So you write it as A dot C is what? A bar and B. Union. Union means OR. Next. In place of B, you have B bar dot. In place of C, you have A bar dot B bar. Okay. So the given circuit, in the given circuit, what did we have to do? A plus B bar dot A bar dot B. Okay, that is what we are working on. Fine. Now you look at this. A bar dot B. A bar is the negation of A. Okay, means opposite of A, intersection B. So basically, A bar dot B means something which is not in A but there in B. Or no, dot, no. Dot means and. Okay. So elements which are not in A and present in B. That is what this represents. Okay. So basically the output here will be something which is not in A but there in B. Compulsorily there in B. That if you take an AND with A, now this has elements which are not in A, this is A, and you are taking AND, then the output here has to be 0. Okay. See, exact set theory formulas, if you remember, you can use them. I don't remember, so I'm trying to answer it this way. A bar means elements which are not in A. Dot B means those elements which are in B. Okay. So elements which are not in A but in B, those that is the output of A bar dot B. If you take AND with A now, okay, effectively you will be doing something like A and elements which are not in A. Then the intersection will be 0. Similarly, the second bracket, if you check now A bar dot B bar means not in A and not in B. Not in A and not in B also. Okay. Or you can split this. No, A bar dot B bar is basically A plus B whole bar. Hmm. Let's not split. Let's take it like this only. A bar dot B bar. So not in A and also not in B. And then you have to take B bar and that. Try to calculate the output of the second one. The second operation is written wrong here. C is A bar dot B only, no? Why did I take B bar there? It should be A bar dot B. Okay, now I think it is easy to answer. A bar dot B means not in A but there in B. So this bracket includes elements which are in B. Okay, not in A but they are in B. Then this is B bar means not in B. And if you take not in B and present in B, then the output of that will also be 0. So the overall output will be 0. Okay, so if you are comfortable with De Morgan's laws, it will be easy to answer these kind of questions where you have to write the output as a combination of the inputs. Instead of writing the truth table of the output, you need to check or you need to express the output as a combination of inputs. But actually, no, in as far as the physics paper is concerned, they don't expect you to know De Morgan's laws. Okay. How they expect you to do it is by writing the truth table only. Like this combination that is there, write its truth table, you would have seen that everything comes out 0. Then you choose the answer as 0. Okay. They expect you to be knowing only that much. But if you know De Morgan's laws, then you know something extra. You can maybe solve these slightly faster. Okay. So fine. That is all there is in this chapter. Just a moment.